Absolutely.
Okay, thank you. Well, let me begin by just giving you the whole talk in one slide. So what I want to do is I want to ask the question, if you have another universe with different laws of nature, and how do they support stars? So what I mean by that is more precisely the following. Suppose I have an ensemble of universes where the forces of nature, the four forces of nature, have varying strengths. That's the only thing I'm going to vary from universe to universe. I want to ask the question, what fraction of those universes will support long-lived, stably burning nuclear burning stars? So in order to do that, what I'm going to do is I'm going to build for you a solid structure model. It'll be a simple one where I use polytropic stars, one nuclear burning species, and so forth. And then I'm also going to restrict my parameter space from 4 dimensions to 3, because as it turns out, when you actually look at stellar physics, there's really only one composite parameter that determines nuclear burning. It's basically the coefficient in front of the reaction rate. And when you do that, you have this 3-parameter parameter space where the parameters are G for gravity, alpha for electromagnetism, and C for nuclear stuff. And what you find is that a large fraction of that parameter space actually supports stars, which is somewhat different than many people have said. So what I'm going to spend the rest of this long period of time doing is to, I have 6 minutes left, I'm going to just give you a flavor for what this calculation actually means. I'm going to show you a lot of slides, but I'm going to go through them quickly. So very roughly, I'm going to start with the usual equations of solid structure, which are 4 coupled differential equations with 3 additional constitutive relations, just like usual. Then to simplify things, I'm going to use a polytropic equation of state. This allows me to solve for the mechanical structure of the star independently of the thermodynamic structure. This is something that you do generally. It's of course a bit of an idealization, but it will work pretty well, as we'll see. What you get is the following mechanical structure. Then the next thing I have to do is put in the nuclear reaction rates. Now, when you have a nuclear reaction with stars, you basically have 2 things. You have a thermal distribution of particles, and then you have Coulomb repulsion. And in order for nuclear reactions to go, the particles have to overcome the Coulomb repulsion by tunneling. The key to that is tunneling. If you actually had real thermonuclear reactions where the temperature is high enough to overcome the barrier without tunneling, bad things can happen, as you see in the lower right. So what you need is the combination of tunneling and whatnot. And when you put all these physics things together, what you get is this coefficient C, which shows up in the nuclear reaction rate. So if you've been paying attention, what you get here is basically 4 equations and 4 unknowns. And then you do a whole bunch of algebra and you get this complicated transcendental differential integral equation. And when you solve that, you can solve for the central temperature of the star, and then you can solve for the radius, the luminosity, and the surface temperature of the star. And that gives you all the stellar variables in a completely analytic model. And the reason why you want to sell your soul to do a polytropic equation of state model and so on to get this completely analytic model is that now that we have it, we can turn the knobs up and down and see what depends on what. Now, before I do that, I have to justify to you that this actually works. So I'm going to use the values of G and alpha and whatnot in our universe, and I'm going to reproduce the Hertzsprung-Russell diagram. This is the main sequence. It's almost exactly the same as the real main sequence. One thing I should say is that I didn't tell you what polytropic equation of state I used. To remind you, a polytropic index of 3 corresponds to a radiative star, and a polytropic index of 3/2 corresponds to either a degenerate star or a convective star, which happens at the lower end of the main sequence. So the 2 lines there are for n of 3 and n of 3/2, and then the middle line is the one where you smoothly interpolate between the 2, which is what real stars do. But you reproduce the main sequence quite nicely in this, and you also reproduce the mass radius or mass luminosity relationship, which the 0th order goes like m cubed. Now the real relationship, when you include all of the detailed nuclear physics in real stars, there's a curvature to this. So it's actually a little bit steeper than this at the low end and a little bit less steep at the high end, but those are the kinds of approximations that we're giving away in doing this completely analytic model. The biggest approximation I'm making compared to the real universe in this context here is that I'm only considering one thing that burns, whereas in real stars you have the PP chain and the Cyano cycle and a whole host of nuclear reaction networks. And I've just boiled that down to one nuclear parameter, which I call C. Now the other thing that I have to tell you is that I've given you a stellar structure model as a function of stellar mass. And I haven't told you what the mass is. To give you the right Hertzsprung-Russell diagram and the right mass-radius relationship, I put in the known mass range that we have. But we have to know why you have that mass range. Well, it turns out that there's a minimum mass that you can have for stellar burning, and that's determined by degeneracy pressure. To remind you, it's counterintuitive that stars live in the range of parameter space where pressure is given by the ideal gas law. So when you get too dense, which means a star that's too small, you are supported by degeneracy pressure that keeps you from having a high enough central temperature, which keeps you from burning. So there's a minimum mass rate, value given by degeneracy pressure. That's the middle equation there. And then there's a maximum mass scale that you get for radiation pressure. As soon as the radiation of the star is so intense that it overwhelms the ideal gas law, then the star is unstable and you can't have stars. So the upper range is given by one thing, or by radiation pressure, and the lower limit is given by degeneracy pressure. So there's this range of stars that's about a factor of 1,000 in mass in our universe. So we basically have two constraints and 2 minutes. So what I want to do is I want to combine those two constraints. So I'm going to consider two things. One is I have to have the minimum mass for stars smaller than the maximum mass for stars. Otherwise I don't get stars. And the second thing I have to have is when I have the minimum mass that I can have, which gives me the maximum nuclear burning temperature, I still have to have a stable nuclear burning configuration. That gives me this equation here, which has to have a solution. And when I plot the right-hand side of that, I see that there's that, or the left-hand side has this particular form here, so that the constants of nature conspire to give you a value above this peak. You don't get stars anymore. And then otherwise you get two solutions, and you want the solution on the right, which is the stable one. And when you do this, I know I'm going fast, you get the following. So I'm going to plot the allowed range of stars in the G alpha parameter space. Here I'm scaling both G and alpha to the values in our universe, and I'm changing them by 10 orders of magnitude in each direction. So this is a 20 by 20 order of magnitude parameter space. And if I fix the value of the nuclear constant C to be the value in our universe, then I get the following curve here, the solid line. And our universe lives here in the middle. So all this parameter space below this curve allowed for stars. So several things you see right away. One is that we're not near the boundary. So all the statements you read in Scientific American about how our universe is fine-tuned and there's intelligent design to produce stars are not quite right, because we could change the value of the constant by orders of magnitude in each direction and still have stars. If you change the nuclear constant C, you go up and down. So since this thing is beeping at me, let me just wrap up. So the bottom line is that stars in other universes are not as rare as people have claimed. If you sort of loosely look at the parameter space that I just showed you, about 1/4 of it allows for stars. And then finally, there's a whole bunch of discussion points. I've constructed a very simple model with simple assumptions. You can immediately find about 30 other things that I should have done that we can talk about. So,
Great. Let's thank Fred very much.